Good morning, everyone. Welcome to some more statistics for us today. This is section 4.2, day 2 on your Stats Medic. So we're going to start looking at some experimental design, at least the experimental design the way that we do this in AP Stats, hopefully the way you do it in your other classes too. So let's go head over there and check it out. So the video starts with This is going to start with something from Good Morning America. I don't remember when this ran exactly. But this Good Morning America clip is going to give us a good introduction into the placebo effect and experimental design as the way that we're going to look at it for our class. So let's take a look at this video.
Rather eye-opening look at human behavior as the social experiment continues on this network. ABC's Nick Watt, the host of a great new show, Would You Fall for That, joins us now from Los Angeles. And Nick, tonight you are putting the placebo effect we hear so much about to the test.
That's right, Josh. I mean, you know that we're all about science on this show. Well, not quite. It's a lot of fun as well. Tonight, the placebo effect. If you think something's going to make you feel better, then it might. And it's summertime, so for this one, we headed to the beach.
We set up a booth on the boardwalk at the beautiful Jersey Shore one sweltering hot day. We told vacationers we're shooting an infomercial for a fabulous new energy drink. We had t-shirts and posters. We even had our very own Whiff Power energy drink banner plate. Oh, and one tiny little secret. Whiff is nothing more than club soda. If you believe a pill will make you better, then it just might. If you believe an energy drink will make you stronger, it just might. Even if it's just club soda. It's a great trick our minds play on us. So all we did was tear the labels off of club soda bottles and stick on our own. Whiffed. Would you fall for that? Would you actually feel stronger after a few gulps? You will be amazed.
What we got going on right here is the Whiffed Energy Challenge. We're promoting a new drink, and it shows immediate results. Who wants to step up and take it? It's totally free.
Whose job?
First up, we invite our passers-by to test their strength on the classic carnival high striker. Swing the mallet, try to ring the bell.
Seven. Now, Keith, that's respectable. It's not stellar. So Shearer's going to give you some whiff right now, and we will increase your performance. Whiff.
So Keith chugs the whiff, and I tell him some highly convincing nonsense about what's in it.
It was discovered by Philip Monroe, who won the Tour de France in 1998.
Then we get him to shake his thing, get the whiff pumping through those veins.
Punch all those distractions out of your life. Don't punch me. All right, yes, punch everything else though.
It's back to the high striker to see just how much stronger whiff has made him. Will he get a better score?
Stand back, boys. Keith is on fire. Yeah! 10.
Ding dong. Just like that, Keith has become a strong man. If you're wondering if we rigged that high striker, the answer is absolutely not. It's the placebo effect at work, and Keith fell for it.
And also tonight, I think one of the most terrifying things I've ever tried to do, I tried to marry a total stranger, someone we pull off the street. I tried to marry that person to one of our co-hosts. The results, shocking, astonishing, unbelievable.
Okay, so that is what happens here with our placebo effect. The guy tries the drink. The drink isn't anything except for a club soda. And magically he does better. So that's the placebo effect. Why do you think people in the video got stronger? That's our first question here. And a lot of times what's happening here is people aren't really getting stronger. They just think they should be stronger. And so their body kind of reacts in that same way. So this is like the power of positive thought. They think they should be stronger, so perhaps they try harder. Maybe another thought here would be this is actually their second time going through the high striker, and maybe that experience made them stronger. But the thing that I want to focus on here is the placebo effect. They think they should behave in a certain way, and so their body, whether or not they want it to, is going to behave in a certain way. So, similar to the video, Mr. Ferrerio wants to use a beverage test to affect that caffeine can have on a heart rate, to test the effect. I'm looking at that and I think that's misspelled. Anyways, here's the initial plan. Measure the pulse rate, give each student some caffeine, wait a specific time, and then measure the pulse rate again. Finally, compare final and initial rates. Just kind of realizing that transition was a little bit fast. This is kind of a whole new topic other than the placebo effect. Because now we're going to be getting into experimental design. So, what are some problems with this plan? What are other variables that could be sources of variability in the pulse rates? So I want to highlight especially this part right here, other sources of variability. And that's really the problem with a lot of experimental design, is that these other sources of variability are going to affect the response variable. And those other sources of variability need to be somehow dealt with in the process of our experiment. So I'll show you what I mean. What are some things that could go wrong here? Well, the first thing is, there could be no other pulse rates that we can use as a comparison. How do you know if a pulse rate is going to go up if you don't know what the pulse rate is usually? So if you don't have a pulse rate to use as a comparison, then you're going to have some problems. A solution here would be to use a control group for comparison. Now, a control group is similar to the treatment groups in that they are going to receive a treatment. However, their treatment is going to be either no treatment, literally not doing anything with them, but they have to be there still for comparison, or they'll get a placebo. If we were doing this with soda, we would give them a decaffeinated soda. So the control group gives the experimenter what we call a baseline for the response variable. Now, one thing that is a common misconception is that a control group is needed for every experiment, and that's not really true. The control group is only needed if you need a baseline comparison. Here's another problem. If we're conducting this, let's say in 5th period, right after lunch, maybe the sugar from the other things that were consumed during lunch are going to increase the pulse rate. That's going to be a problem because that additional sugar is going to act as a confounding variable. We won't know whether or not the increased pulse rate came from lunch or if it came from the Coca-Cola. Those two are confounding each other. We don't know which one is affecting the response variable more. Now, if there are confounding variables that you know about, that the experimenter knows about, the way to deal with that is to control those other variables. And what I mean by that is, let's just make sure that everybody either doesn't have lunch or hasn't eaten in the last, 2 hours, or give everybody the same lunch. So what we're doing is we're controlling the other confounding variables. Okay. Now, control is different than control group. They are kind of not the same thing. So it's unfortunate that we have to name them with both the word control, but things are what they are, and unfortunately, that's another bit of confusing terminology. So control group is not control in the sense of controlling variables. Great. So what else can go wrong? Well, kind of with that whiffed water in the video, maybe the subjects know they're getting a caffeinated drink, so whether they want to or not, their body's going to behave in the manner of getting a caffeinated drink. This is like the placebo effect, or I guess this is a little bit like a Pavlovian reflex. I'm not 100% sure if this qualifies under that, but yeah. If you know you're getting caffeine, perhaps your heart rate is going to go up. So we need to find a way to distinguish the difference between those things. This is where blinding comes in. Blinding is when the subjects do not know what they are getting. They don't know if they're getting actual Coca-Cola or if they're getting a decaffeinated Coca-Cola. In successful blinding technique, both subjects are going to receive a very similar looking treatment, and they will have no idea which treatment they received, whether they received the caffeine or a placebo or even something else. Who knows? That's what we use blinding for. It's to control all of those controls those things that are going on in your brain that are people don't even know about. So if we don't tell them what they're getting, then we have a better job. We have a better chance of dealing with those situations. So there's also a double blinding thing, which I'm sure we'll get into eventually. But double blinding is when the subject doesn't know what treatment they're getting, so their head space is all similar, or the subject's head spaces are all similar. And number two, that could be a double blinding, where the subjects don't know what they're getting, and the person observing the subjects don't know the treatment that the subjects received. Sometimes, that those head effects could happen with the experimenters. So we want to find a way to control that as well. Go back up to your list in number 2 and find a proposed solution for each of those problems. Wow, I think we kind of did that. The first thing for the comparison was to use a control group so we would have a baseline pulse increase or pulse rate. For those additional sources of sugar, then maybe we should only use subjects who have not eaten or drunk in the last 2 hours. Lastly here, we're going to not tell the subjects if the treatment they received was the caffeinated treatment or the non-caffeinated treatment. Just another thing that I thought about here with blinding, just because you have an experiment does not mean you have to use blinding. Blinding only needs to be used if there is a possibility of a placebo effect going on. So just like control group, we only need to use blinding for in certain experiments. Certainly not for every experiment that we do. Now next we're supposed to design an experiment to test the effect that caffeine has on heart rate. And a lot of times we like to start this with a diagram. So let's take a look. Let's diagram this out. So let's start off with a group of 50 students. It doesn't have to be 50. It just has to be some large number. You don't want to do 2 students, and you probably don't want to do 1,000 students because then that gets a little bit unwieldy. But 50 students sounds pretty good. The next thing we need to do is we want to randomly assign them into 2 groups. Group 1 with 25 students, Group 2 with 25 students also. Ideally, the 2 groups should have similar sizes although that's not always 100% necessary. If we had it with 27 students and 23 students, yeah, that would still be a valid experiment. But, you're just trying to shoot so that you're somewhere in the middle here. Now, the random assignment is important for us because what it does is it takes any sources, any confounding variables that we don't know about, and it distributes them, hopefully evenly, among group 1 and group 2. Okay? So there could very well be other sources of or other variables that are affecting the pulse rate that we don't know about. So we can't really do anything to control them. So the best thing that we can do is try to make sure that group 1 and group 2 both have the fair chance of receiving that confounding variable. So we start with the 50 students. We randomly assign them into 2 groups so that confounding variables are, somewhat mitigated. And then we take the 2 groups and we apply treatments to them. Group 1 is going to get treatment 1, which is going to be the caffeine drink. And group 2 is going to get treatment 2, which would be the non-caffeinated placebo drink. I don't know what it is, but that's the treatment that we're going to get. And at the very end here, we're going to compare pulse rates. At the end of all of our experiments, we're going to be doing some kind of comparison. So keep that in mind. Notice how this is kind of like a flow chart. We start with the 50 students. We split it into 2 groups. Group 1 goes along to the top branch and takes caffeine drink. Group 2 goes along the bottom branch and takes a non-caffeinated placebo. And at the very end, we compare pulse rates. So that's the experimental design. We do need to write it up a little bit, so let's kind of try to figure out how to write this up. So let's start with the 50 students, and we're going to do a random assignment. That's here. Start with the 50 students, and the next is that random assignment part. So this is going to be very similar to the SRS. It is an SRS, really. But it's going to be a little bit more streamlined to help us out with this process. And what I mean by that is, rather than giving them a number between 1 and 50 in order, we're going to assign each one a random number between 1 and 50. So we're not going to go in order. We're just going to say, hey, you get 2, you get 13, you get 12. So randomly give them a number between 1 and 50. And that's going to allow us to create our groups, group 1 and 2. 1 through 25 is going to go to group 1, and 26 through 50 are going to go to group 2. Now, because the students were given a random number between 1 and 50, then there shouldn't be that satisfies the randomization that we've been talking about. And it's probably good to note here that this should be no repeats. Okay. A popular way to do this is just to take scraps of paper. Each of them have a number between 1 and 50. Put them in a hat and have each student pick a number. That's totally fine. I don't know if you need to go in that much detail, but as long as you say you assign them a random number between 1 and 50, no repeats, you should be okay. So looking at our tree diagram, the next thing we're going to do is, we've just assigned the groups, so now we're going to go to the treatments. So we're going to describe the treatments. Okay, treatment, group 1 will take 8 ounces of the caffeinated drink. Group 2 will take 8 ounces of the non-caffeinated drink. Now, I just kind of made up that number, 8 ounces. There's nothing significant about it other than 8 ounces is a cup, and it's a pretty common unit of measure for liquid things. So we are done with the next part here, and then as we're reading from left to right, the next thing here is to compare pulse rates. So we write a little bit about comparing pulse rates. So after 5 minutes, take each student's pulse rate and then compare the average pulse rate from group 1 with the average from group 2. Now, a few things with this. I have totally made up the number 5 minutes. We just need some kind of a time when we're going to, take the pulse rate. With this design, since we're taking in quantitative data, the thing that we're going to want to compare is the average pulse rate from each groups. So I try to make it a point to say that. Make sure that you write down that you're comparing an average from group 1, in this case the average pulse rate from group 1, with the average from group 2, in this case the average pulse rate from group 2. So once you're finished with this is the design. I don't know where I was going with that, but this experimental design has a name. This design type is called a completely randomized design. Why is it completely randomized? Well, the only thing to do really is to randomize the students into the treatment groups. We didn't do anything else other than randomize. So hopefully everything has been, all the variables have been randomized. This is different. We're going to be looking at other design types in future parts of this section. But this is actually the easiest one to do. It may not be the best one for every experiment, but it certainly fits a lot of different types of experiments. So I want to emphasize to you that your description has to contain those 3 elements: the random assignment, the treatments, a description of the treatments that each group will take, and number 3, an indication of what is going to be compared. So random assignment, treatments, and comparison. Now that's kind of a lot to take in, so take your time with it, and we'll go on to our big ideas here. Control group is going to be used to provide baseline data for comparison, and I want to emphasize that that's not always necessary. Sometimes you don't need to know what the baseline is, you just need to measure the effects of something. If you need to know if it does better with than no treatment at all, then you're going to want to use a control group. But if you already know that your treatment is going to be better than no treatment at all, then you don't need a control group. The blinding, like we're reading here, this is when the subjects and or the experimenters, the people who interact with the subjects, are unaware of the treatment assigned. And that just makes sure, well, with single blinding, that helps us with the placebo effect. And with double blinding, that helps us with, sometimes the experimenters will, perhaps exaggerate the effects if they know that a subject was actually getting a treatment. Can happen. Definitely, if you are doing an experiment like this, then perhaps you want the experimenters double-blinded just so that, anyone who criticizes criticizes or examines your experiment won't be able to say, oh, well, the experimenters knew that they were receiving, so they gave them better marks. Who knows? Next, the placebo effect is going to be when a fake treatment works. Okay, now that might happen because the subject is actually thinking about what's going on, thinking that they should perform better with the treatment. Maybe it'll just be the body's natural reaction. Maybe it'll be experience. But there's a few different reasons why the placebo effect is a thing. But since you know it's a thing, you're going to have to do something about it. Now, we didn't talk about this explicitly, but the principles of experimental design, they are there to mitigate the effects of confounding variables. So everything that you need, everything that you do in your experiment needs to touch on all 4 of these, and we'll take these a little bit slowly. So let's compare and contrast that with the experiment that we just designed. First of all, comparison. Are there 2 or more treatments? Let's take a look. And here we have group treatment 1 with caffeine and treatment 2 with non-caffeine. An experiment is not an experiment, or at least a valid experiment, unless we have 2 or more treatments to compare. Next, random assignment. Was there a chance process to assign treatments? And remember, that's going to be because we want to distribute the confounding variables among the groups. And yes, here's our random assignment. Okay, here is our description. We gave each student a random number between 1 and 50. Control. Did we keep all the variables constant? Did we try not to introduce any new confounding variables? And that's kind of hard to see here, but notice that we did start off with 50 students. So we could have perhaps written more here about the description of the students. In fact, let's do that. Start with 50 students, none of whom, none of whom have eaten or drank in the last 2 hours. Okay, so that helps us definitely with that whole thought of control. So, did we keep all variables besides the treatment constant? Yes, we did. We tried to make sure that all the students did not eat or drink in the last 2 hours, and that was our control. Also, having students here is an instance of control because caffeine works differently among different age groups. And if we say all students, then we have some reassurance that the caffeine is affecting the same age group. And lastly, replication. Did we use many experimental units? And that's going to be to average out the effects of confounding variables. And yes, we used 50 subjects. So we have done all of the, or we have touched on all the principles of experimental design. So we can be rest assured that our experiment is pretty good. There's a check your understanding here, which you will have to do on your own, but it's a pretty good one. So that's all we have for you today. Thanks a lot for coming with me on this Stats Medic Section 4.2 Day 2. The experimental design, of course, is a lot different than the rest of the math that we do in statistics, and really a lot different than any of the math that we do in other math courses. So this gives, if you're not particularly mathy as a person, this is a good place for you. This will be a good section. So I'll see everyone later, and have a good day wherever you are.